last Friday when we were basically doing our recitation. This is related. So this was at the very end of last time. You guys probably didn't take notes on it, but I'll just put here, recall. The system was a mass on a hinge here, and it was supported by a spring. You guys remember that? And it was doing the frequency of oscillations. So this was a bar, spring, and G was pointing down here. Now what we can look at first, and what's related to this one, in a simpler vein, so I'll write or consider this very basic system. We've got a mass on a spring like this under gravity. This is actually just a more complicated version of that a little bit, but this one has some interesting features. So I can let the positive x-axis be in the up direction, and then the question is, what's the kinetic energy of this system? It's just a half m x dot squared. We're just going to have this mass bobbing up and down. Okay. What's the potential energy of the system? This one actually has two parts. Namely, there's the gravitational potential energy, mgx plus an arbitrary constant, right? And what else? Half k, and we can even say half kx squared. We just have to put this x equals 0 when the spring is relaxed. So if I were to hang a mass from this relaxed spring and gently lower it, it would come down to some lower equilibrium position, right? So that's a legitimate thing. mgx is just plus with respect to an arbitrary constant, or up to an arbitrary constant, 1/2 kx squared, because I've chosen the x equals 0 where the spring is relaxed. Okay. So what does the graph of this potential energy look like? We'll just graph it right away. You guys remember our trick for graphing functions? We look at them separately. So this is just a straight line, which I'll do as a dotted line. And by the way, x can be positive and negative in this problem, right? So this is just a straight line, and what about this one here? Parabola, yeah. Let's do it in red. Try to be a little bit systematic here. And if you add these, it's going to be shifted in the positive direction. So if you add these two, what you're getting is something that starts out linear and grows like this. Okay. Should actually be smooth here. But this is legit, this is pretty good. You can make it a little bigger. So what do we see here? This is also a parabola. It's really just shifted somewhat, and it has a equilibrium point here on the negative axis, just as I discussed, right? If I lower this thing down. So it's got an equilibrium at x of 0. And of course, if we're doing a Lagrangian, we can do t minus u. We'd have a legitimate Lagrangian. But say we're doing small oscillations. You guys remember the small oscillations frequency formula? So I'll put up here, we're doing small oscillations. Quite possible we had this one up on the board last semester, it's pretty standard. So if we're doing small oscillations, we say omega squared k over m equals u double prime of x naught over m. Okay. And here comes the punchline. So here, u prime of x is equal to mg plus kx. Now, x0 is the point where u prime vanishes. First derivative criterion. So u prime of x0 equals 0, and that tells us that x0 is equal to minus mg divided by k. Same thing you get with a free body diagram. Minus mg over k. What about the second derivative? This is the actual punchline. U double prime of x is simply equal to k. So I already took one derivative here. And this shows that this system frequency is independent of whether it's in gravity or not. And that was what Sam was alluding to with this system here. Remember? But it wasn't as clearly set up. But we were running out of time last time to really tease that out. But that's the reason. So that's the reason that system's independent of gravity. And you see, it doesn't really depend on those things canceling out as they did last week here. It just depends on the fact that the second derivative here is purely equal to k. It doesn't matter about the position k. So that's a good problem. It's a good one to keep in mind. We're talking about oscillations, and that this potential is just shifted, the parabola is just shifted and down. Otherwise, it's the same parabola. Good. So where are we with our Hamiltonian stuff? I'm going to continue on a bit with the Hamilton mechanics, and then I'll just kind of list what's going on for the exam on Wednesday. What's the last thing we have in Hamilton? Any suggestions there? Ooh, I know we're just starting with that topic. I think I'll just write up the list of steps. And that takes us right through the Lagrangian aspect. So since it's been a couple days, let's just put Hamilton mechanics right here. Because the first steps are also Lagrangian. So the first step here is we have the mechanical system. Mechanical system, and we need a set of coordinates and their generalized velocities, and then we can construct L equals L of Q1 to Qn, Q1 dot, Qn dot, and P. So yeah, we need this for the exam on Wednesday. We have to be able to construct the Lagrangian. We'll do a little bit of examples as we go through this. But what we have at this stage of the game is the definition of P sub I EL QI dot. That's the generalized momentum. And it plays a role in the Lagrangian mechanics as well. And of course we have the equations of motion here. And the equations of motion. Now this I'll actually put parenthetically because we don't need to generate the equation of motion. We need this expression. And then the energy is the sum of EL QI dot minus L. we can, right, this is P sub I. If we can express this thing purely in terms of P and Q, so this very self-same thing, I'm just gonna write E goes to H, if you can express it in terms of coordinates, generalized momenta, and time. So if you can do this, then it's the Hamiltonian. So it is the Hamiltonian. And the equations of motion for the Hamiltonian, and yeah, generally speaking, H is T plus U in the most of the basic cases. If we do a relativistic one, it's going to look different. But yeah, this was T minus U, this is T plus U, properly expressed. And then we have the new equation of motion, Qi dot equals partial H with respect to P sub I, and P sub I dot partial H with respect to Q sub I. And these equations are now first order. So we have 2n first order equations. And then we just have to get used to doing this. But with our basic systems that we've been studying, we plug one into the other, we're going to get the Euler equations back again. Okay. But having them in this form of first order equations has some great benefits downstream. So I gave an example of this. I want to do a couple more. But these are called Hamilton's equations or the canonical equations. And we got a couple. Did we assign any homeworks or were there just recommendations?
Yeah, you assigned a couple.
For this coming week? Yeah. Okay, so the ones I assigned were just basic applications. You wanted to, I'll put here examples, and we'll look at some of these. So, projectile motion, central force, are the basic examples. And we can also do spherical polar coordinates. We can do spherical polar coordinates as well, just do these constructions here. I think what I'll do is the projectile motion example. Handle both of these. But before we do that, we'll do the general case. So we've got this whole list here. This is how we set things up. Now, actually, I'll tell you what. Let's set up the projectile motion problem. As the really basic one. So, going through that list, we have X, Y, and Z, right? Projectile motion problem, we got X, Y, and Z. I'm going to do it this way. I'll do X, Y, and Z. And we know we can just restrict it to 2 coordinates if we want to. No, change my mind again. Change my mind. X, Y, Z. Good. So then the Lagrangian is a half n x squared, y dot squared, plus z dot squared, minus mgc. Right? Potential energies, c is the up and down direction. So we've got the Lagrangian, and the piece of x is equal to dl dx dot dl dy dot piece of z dl dc dot. And E, we're going to have a half m x dot squared z dot squared plus mgz. But we're going to make these substitutions here, right? This was mx dot, etc. So we can make this Hamiltonian just be ex squared over 2m plus ey squared over 2m plus ez squared over 2m plus mgz. This again, if we pursue this all the way through to the equations of motion, we're just going to come full circle. But I just want to bring out an important point here, and that is the cyclic coordinates here works the same way as it does in Lagrangian mechanics. So remember, this general form would be h of x, y, z. Those are our q's. Ex, ey, ez. And what's cyclic in this Hamiltonian here? The coordinates are cyclic.
We're not really in terms of x and y.
That's right, we don't have x and y explicitly. So x and y are cyclic. And then the canonical equations here are Ex dot is equal to minus EH dx, dy dot minus EH dy, Ez dot minus EH z, and this is equal to 0, and that means Ex to the constant. Same thing here, equal to 0, and that means Py is equal to constant. Leave a little room, I'm about to give it a name. Here, this is equal to minus mg, that's nice. So Pz dot is not equal to a constant, okay? So this, of course, is just free fall in the z component. What we're going to do is call this alpha sub x. We're just going to define this in alpha sub y. For some reason alpha gets chosen here. Because having analyzed this, we can now say that this Hamiltonian turns into h of c and piece of z, and then I'll put a semicolon here. And these two conserved quantities play the role of parameters. So this is something that's possible in Hamiltonian mechanics. You can simplify the problem, we call it a one-variable problem, with these constants here. You're not allowed to do that in the Lagrangian method. You're not allowed to just replace these things. So what we would have now H would be alpha x squared over two m plus alpha y squared over two m plus e sub c squared over two m plus mgc. These are no longer dynamic variables. You still have your full set of canonical equations, you can go solve the whole thing. But that allows a certain simplification. We've done this before in last semester when we did the central force problem. So I could come back to the Lagrange's method and the central force problem. So yeah, I'm gonna put a couple words here, but yeah, this is the new Hamiltonian actually started to analyze the system. So I'll just write alpha x, alpha y are parameters, they're no longer dynamic variables. Okay. Yeah. Okay, I'll leave that right there. Let's go back to the central force problem, Lagrangian. That was projectile motion. By the way, actually, before I leave this, let's make sure we still remember, we still have the other three canonical equations. Okay, I just wrote three of them down to make my point here. Let's add this to the mix, yeah, we'll add it here. So we also have, remember, Q dot equals GH BPI. So yeah, we still have x dot equals BH BP sub x, which in this case is now alpha x over m, right? Cancel the 2, alpha x over m. That means x of t is equal to alpha x over m t plus beta x, and so on. Okay. So yeah, we still have those, and we have them in y, and then z you have to solve with this equation. Okay, that's as much as I'll do. I may ask more about this problem, but we'll do it in a moment. Okay. So let's look next at the central force Lagrangian. And the central force Lagrangian goes, we'll cut straight to the chase. We have 1/2 m r dot squared r squared p dot squared minus u of r. And then we have p sub r equals dl dr dot. And r dot, that's the one. And then p sub easily construct the Hamiltonian as well. Just, basically, we do H equals P plus U, and then we just substitute the R dot P star over M. Actually, let's do this. Then the energy. See, this is what we did last semester. The energy of the central force problem. It came out of T plus U. If you guys may remember, it was 1/2 M R dot squared, this one, plus 1/2 M R squared P dot squared, plus U of R. And that crucial step that we did last semester was the 1/2 mr squared phi dot squared. We made that substitution with the phi dot. I'm going to use piece of phi squared over 2mr squared plus U of R. Anybody remember what we named this thing last time around? What letter did we have there? Instead of piece of phi. This was our lowercase L squared. Remember L squared here? Let's actually go back to tried and true. What we did was we have that. L squared over 2mr squared. And if you remember, then we looked at this combination. What do we call this one here?
U effective bar.
That was the effective potential of R. Essentially what we did was, well, the Hamiltonian method will do exactly the same thing. So if so this is what we did for the Lagrangian method. I'm just gonna go up here and say Hamilton. So the Hamilton method will have H instead of E. The R dot, P sub R over M, so we'll have the P sub R squared over 2M. It'll have this P sub phi squared over 2mr squared plus U of R. Same situation. This here, because we have a cyclic coordinate, I could have just called it alpha sub phi, or I could have called it lowercase l, right? And then we'd be exactly where we were last semester. Not quite exactly. We would take one more step to return to this equation here, but that's how we would actually solve it. So if we're solving this with Hamilton's method, we're actually going to go right back to here. Okay. And remember, what we did was we did the quadrature here and solve the equation of motion that way. So it's all familiar ground in that regard. And what we see is that we have the same physics with the big normal coordinates. Okay? The same physics with the cyclic coordinates in Hamilton's method as in Lagrangian method. Okay, let's see what else. I think at this point, I'll turn to the review for the midterm exam. So you can see that this is already a nice review of the Lagrangian method, particularly with cyclic coordinates. They work the same as Lagrangian mechanics. Okay, good. But I don't think we'll put this on the exam. We'll save this for later. So now let's see what we need to know for Wednesday. I should say, was our Kepler problem. Okay, so I'm just wanting to put this right back into context. That was looking at the Kepler problem. So yeah, if we did the Hamiltonian method of the Kepler problem, we'd come right back to where we were. Okay, good. So in terms of our review, here's what we have to look forward to. We can do something on the variational calculus, which I'll remind you guys of. And from the variational calculus, we go to the Hamilton's principle of least action. And that gives us Lagrangian mechanics. Number one, I can come up with a nice little problem. Number two is just for us to be aware of Lagrangian mechanics, of course, we're interested in, and then small oscillations. So, and that's as far as we've got. So, variational calculus, we get a nice problem. I'll remind you guys, this one was if we had integral f of y prime x dx. I'm just going to write minimal, maximum, saddle. So these are those scenarios. Then we have two things. We have d over dx partial f y prime equals 0. And that's the Euler's Lagrange equation before we had the mechanics, just this geometric type problems. And if f is not explicitly a function of x, then we have df y prime minus f equals a constant. So what you have here is a situation where you can reduce something to a quadrature and maybe solve it. So I'm just going to remind you what the example was of this, and I'll see if I can come up with a nice one for us on the exam. One of the examples was the catenary, no, minimal surface of revolution. So the minimal surface, you had some function y of x, and you sent it around, and now it generates a funnel-shaped surface. You guys remember that? And then we had this little d area was 2 pi x dl, and so the area integral was 2 pi x root 1 plus y prime squared dx x1 and x2, and that function f of y prime and x was had Euler's Lagrange equation, correct? If we have one without the explicit x, then we would be using this equation. And it's important, if you do have one without the explicit x, and you use the Euler Lagrange equation, you're just gonna get yourself in trouble. You really have to go to this Euler's second form. So that's one idea that we have. And, you know, we did a number of these. So I'll give you something good in that regard. The second thing we want to set up is Lagrangian mechanics. So setting up a Lagrangian and then getting its equation of motion. So if that was one, then the next one here we want to construct L. The example I have for this was if we had x was r theta minus r sine theta, y was r cos theta minus r. Anybody recognize this thing here? Good old inverted cycloid. And you know, if this was x and y and we had gravity, then we had a few steps to do to turn it into Lagrangian. And then we could keep on analyzing it, right? So this was one that we've done, and it has all the ingredients here. If we have more degrees of freedom, then it gets a little more involved. And what you could do on this one is construct small oscillations Lagrangian. And for this one, I'll just remind you, it turned out looking something like this: a half m times 4r squared actually I'll instead of the small oscillations one, let's just remind ourselves what this one would have looked like. We ended up with a half 2m 1 minus cos theta minus mg r cos theta minus r. So we have a bunch of stuff going on there. And then, you know, you could get L small oscillations, etc. What if we have more than 1 degree of freedom? More than 1 degree of freedom, I would give this example. When we have the mass connected to the little mass, right, the pendulum on this track here. If I do one of these, you know, we don't have that much time on the exam. I'll possibly set something up like this and have us just do a couple steps on it, right? Then we can come back and finish her up when we have time. But this one's really important in that you know you have to. I call this one capital X, and then little x was capital X plus L sine phi, right? And then we had to do x dot capital X dot plus instructions and get kind of involved. But if I get you one of those types, then, you know, just take it a few steps carefully, start constructing the Lagrangian. Because, you know, you've looked at the double pendulum, that takes a little more time than you want to do right in the middle of an exam. But yeah, we want to be able to construct some Lagrangians and analyze them. So I'll say construct L, and then I'll say, you know, find L small oscillations off of that original L. At which point we can just cut to the formalism. Let me erase up here. We can go to the formalism that takes us all the way to the frequencies. So if you can find L small oscillations as this form, I'll just remind you guys, Mij xi dot xj dot minus 1/2 double sum kij xi xj, right? So it has that form, but you don't necessarily have to write it out this way if you're able to just get these coefficients, right? To get those individual matrices, and then the Kij is the d squared u dqi dqj q0. Because if you can just get these two matrices, then we know we can get this characteristic polynomial with the subscripts here. And that's generally as far as we want to go. The next step where you actually solve the characteristic polynomial, that's a separate thing. If you write it out, you can often do some good analysis. This one gets a plus sign, by the way, plus equals 0. So that's really what we're looking at. We're looking at a variational calculus problem of nice basic nature, and then setting up some Lagrangians, calculating them, constructing them, and then doing some small oscillations. And that'll be enough. That'll be enough for our 50 minutes. I've got 3 classes taken